Buenos días a todos, muchas gracias por venir a la 8ª edición de los coloquios Curie. El acto se desarrollará en inglés, así que cambio de idioma. Thanks for coming, and we hope that this colloquium will be very interesting and exciting for the wide variety of scientists that I can see in the audience. We have for this edition the representation of the CSIC. It will be Don Federico Monpean, who is Deputy President for Scientific Programming. So please, Federico, you can say a few words.
Thank you very much, Rebecca, and thank you very much, everybody, for coming to this Sklodowska Curie Colloquium. Thank you for the organizers for extending the invitation to the CSIC President, Professor Rosa Menendez, and on her behalf I would like to obviously welcome you, give you a very warm welcome to the Instituto Rotational and to CSIC. And I personally am very glad to have this excuse to complete the paperwork for, let's say, at least 1 hour or so, and to try to listen to some very exciting physics, like the one that Jon Marangos is certainly going to present. I've been given the instructions of actually talking for about 3 minutes, and I would like to take this opportunity to address. I think that the audience is pretty general, not only people from CSIC, but I would like to somehow convey the message that at CSIC we're actually very conscious of the necessity to keep the scientific instrumentation and the scientific equipment that we have in the laboratories up to date, so that actually we can do very competitive science. We have done quite a lot of an effort during 2018, where we have been trying to put together different sources of funding so that we could try to maximize the impact at all the laboratories and all the institutes at CSIC. And specifically here at the Rotational Institute, we have, I think, been quite successful in trying to put together a significant boost for the Laboratorio Manuel Rico, the nuclear magnetic resonance laboratory. But this is a kind of activity that we are contemplating to extend. We would like to actually give this boost to the instrumentation that is needed in the laboratories, and we would probably be asking you to join effort with other colleagues with whom you may be competing, but at the same time, when we come as an institution to formulate what are the requests for instrumentations and how we can use our the funding resources that we have, it's very important that we gather together and that we are able to propose the purchase of a significant number of pieces of equipment that are of a similar entity, so that we can get best offers from the suppliers. So this is an exercise that probably we'll be asking you to do during 2019, and hopefully we are able to complete it so that you can have in your laboratories instrumentation that is much better, and probably is going to obviously have an impact in the kind of science that you are doing. I think that actually we are here gathered in order to listen to Jon and the exciting science that he is going to present. So from our point of view, this is all we wanted to say, and we thank you very much for the opportunity of attending this colloquium, and actually we hope that you will find the talk is very stimulating for your own science. Thank you.
Thank you very much, Jon, for coming to Madrid in the name of the commission that organizes this series of seminars. We're really grateful that you made the effort of doing this ultra-fast trip to Madrid to tell us about your research. It's a pleasure for me to introduce Jon Marangos. I've known him for many years. I've been part of his group for almost 3 years, and that was a really fascinating period in my research life. Jon Marangos is very much an Imperial College person. He graduated in physics in Imperial College and also did his PhD there. Although he has had other positions, for instance, he's worked in NIST in the USA as a visiting researcher, and also in Tokyo, in the University of Tokyo, as a visiting professor. He was the head of the Quantum Optics and Laser Science group in Imperial College London, and he is now the director of the Blackett Laboratory Extreme Light Consortium, and as he just pointed out to me that the name changed, they are now the Extreme Light Consortium, which is very indicative of the type of research and the direction that they're taking in their research. He has obtained many honors and really important projects, for instance, an advanced ERC grant devoted to attosecond physics. And his main research interests, correct me if I'm wrong, John, are, well, intense laser-matter interaction, what happens when matter is exposed to very intense electric fields produced by lasers. Nonlinear optics, it's related to that, no? The generation of coherent short pulses of light through nonlinear processes. And also very much he's a world leader in attosecond physics, this last frontier of time resolution and dynamical processes. So he's also involved in free electron laser science, as I think we will see from his presentation. It's a pleasure and an honor to have you here, John. So please, this is your turn now.
Thank you, Rebecca. Thank you so much for the invitation. It's great to come back here. I was just saying I first came here 32 years ago as a young scientist, and quite a bit's changed since then. I'm still a scientist though. So, and back then I was working with Marta Castillejo, Angel, and Margarita down in one of the basement labs, I recall, and it was a very, very nice time, and it was the start of a long collaboration. So what I'm going to talk about today is ultrafast X-ray science, and to give you a taste of where the field is going, and in particular to introduce you to the capabilities enabled by new X-ray light sources with very short duration. So the two I will talk about, the two that are leading this emerging area, are high-order harmonic generation driven by strong field lasers and X-ray free electron lasers, which give us these very short pulses of intense X-ray light. So let me begin by telling you why we're interested in this field, and of course many of you immediately appreciate that we're interested in the atomic scale in matter, and the atomic scale in matter is at the sub-nanometer spatial scale, and so we're interested in very small distances and very small changes, but nevertheless changes that can be very significant. And those changes in maybe a phase change in a condensed phase system or a chemical reaction in a molecular system happen typically on very fast timescales. And so one would like to be able to study the structure of the material and at the same time understand the dynamics. So just to sort of reinforce that point, if we consider a familiar molecule like benzene, the interatomic distances are on the order of 0.14 of a nanometer, and that sort of establishes the structure. But also, we have to really know about the electronic structure, what the electronic quantum states of that system are, and of course, the positions of the atoms and the electronic states are intimately connected, they're completely correlated, so you really need to understand to understand the full structure of the system, you need to understand the full quantum behavior of both the atomic and the electronic components. And so the main point of the work I'm interested in is not just to understand the structure. We've understood structure of matter. We have very powerful tools for understanding the structure of matter in the form of X-rays and neutrons and electron scattering that give us very precise structural information, and that gives us deep insights into also the function of those materials. But there are some cases when, in particular, one has a non-equilibrium condition, an excitation that leads leads to a chemical reaction or a phase change, where we would really like to be able to follow the structure dynamically. We would like to understand both the structure and the dynamics. And that's really what I'm going to be talking about. So trying to extend these static structural measurement tools to make them able to follow structural dynamics and at the same time track electronic state changes in the material. So the sorts of timescales I'm interested in are at the relatively fast end of this spectrum. So this was a graphic that was prepared by a colleague of mine, Melzier, a couple of years ago, and was meant to sort of encapsulate the idea that we're interested in making so-called molecular movies, and we're interested in this fast timescale part of the movie. But of course, just to get into context these timescales, the sorts of things we're interested in are things that are happening on tens of femtoseconds to tens of attosecond timescales. So an attosecond is 10 to the minus 18 of a second, so a 10 attosecond timescale is something like 10 to the minus 17 of a second. So in relation to the sort of timescales at which we operate, I would say maybe the human heartbeat, which is 1 per second approximately. I'm a physicist, so I'll give that kind of approximation. 1 per second. And we can think about, well, okay, how is that related to this very fast timescale of 10 to the minus 17? Well, it's almost the same proportion on this logarithmic scale as the human heartbeat to the age of the universe. So that's really how brief some of these things we're interested are. They really are going down to this really tiny timescale. We'd like eventually to be able to measure electronic events there. But most of what I'm going to talk about happens a little bit slower than that. It happens around the femtosecond timescale. So for that we need probes that can access that femtosecond timescale. So what we're interested in then is to look at something like this metal-ligand complex. This is one that's implicated in various photocatalytic events. It's a largish molecule. It has a metal center with surrounding molecular structures. And what we're interested in, of course, is the static structure, which is the arrangement of the atoms with respect to each other, and of course the electronic structure associated with that. So these bond angles, bond distances, and all of that. That's the structure of the matter. But we're also interested in what happens when you have either changes induced by thermal fluctuations or changes induced by excitations like light or electronic excitations that cause this to go into essentially a non-equilibrium quantum state, and then it evolves, and it can evolve quite quickly, and in that evolution we can expect to have changes to the structure, electronic transfers, very fast electronic transfers potentially between different locations within the system. So, in the spirit of keeping this at an introductory level, I'll say a few words about these sorts of timescales for these changes. And the sorts of timescales for these changes are set by the rotational, vibrational, and electronic timescales of what goes on in the mass. So we think about a simple molecule as a quantum rigid rotor. We've got an idea of how that's quantized. That gives us an idea of its energy levels. It gives us an idea of the rotational timescale for a molecule. Typically, the rotational timescale is going to be given by 1 over the molecular constant, h bar over the molecular constant. So for a light molecule like the hydrogen molecule, that has a rotation time of about 100 femtoseconds. Fast, but on my scale, still a bit slow, but there are much slower rotations than that. Big molecules rotate, of course, very slowly, picoseconds, even tens or hundreds of picoseconds for those motions. And you know, such motions, such rotational motions are even happening in very big systems. So here's an example from the cyanobacteria phytochrome, where there's a rotational mode that's a part of its function. Then, of course, there are vibrations, changes in the internuclear separations and bond angles in an oscillatory way. And those, of course, can be looked at in terms of the quantum harmonic oscillator and its states, and one can also work out the timescale associated with the natural frequency of those modes. And again, hydrogen H2, the hydrogen molecule has the fastest timescale vibrations. The oscillation time of the H2 molecule is 8 femtoseconds. That's the natural frequency is inverse of the natural frequency, about 8 femtoseconds. But then there are much slower motions associated. Whoops, I pressed the wrong button. Whoops. Okay, that was good. There are much slower motions associated with vibrations, and here's an example of a sort of an isomerization. An isomerization is not really a vibration, but it's on the same kind of time scales of vibration. The time it takes the nuclei to move around in the chemical reaction is on that kind of vibrational time scale of hundreds of femtoseconds. But there's also, of course, the possibility of electronic motion. Now, electronic motion can be very fast. If you think of Bohr, and I think of Bohr a lot this week, because I lectured my first year undergraduates on the Bohr atom yesterday morning, and I was explaining to them that an electron in the first Bohr orbit of the hydrogen atom orbits in a period of 150 attoseconds. Of course, we know that the real quantum world doesn't quite look like that, but there are examples where you can see very fast electronic motion going on in materials, particularly if you excite them out of equilibrium. So here's a calculated example of electronic hole dynamics induced in a dipeptide molecule. So this calculation was made some years back, not by my group, but by Mutley and Levine. And it shows how a sudden excitation of a hole at one end of this molecule results in a charge migration, a hole motion, oscillatory hole motion, from one side of the molecule to the other and back in a sub-femtosecond time scale. Really, really fast. And this idea that you can get really fast charge migration in molecules is excited and stimulated a lot of work in attosecond science to understand how that really behaves and how that may have implications in future directions in chemistry and control. So electronic timescales can be very fast, but this picture is not the whole story. Over the last decade or so, we've really begun to understand that the coupling, the electron vibronic coupling in the system really is very critical and can also happen and influence things on a very fast time scale. So in fact, a more complete picture is emerging that we have basically, and I think this is a statement of anyone who's a chemist in this room will agree with this statement, essentially we have chemical, also physical changes, where the electronic, the vibrational and the rotational modes evolve in a highly correlated fashion. They really are linked together. And so we need some tools that will unpick them, that will allow us to make measurements that can look not only at the positions of the atoms, but also at the electronic states in an instantaneous way, and actually give us a complete or a more complete picture on these evolving systems during a chemical reaction or a phase change in a condensed phase system. And some of the important problems of these ultra-fast timescales, things that we would like to understand better. A lot of work, of course, has been done, and let me stress, there's been a huge amount of work done on ultra-fast spectroscopies of one sort or another. I know there are many ultra-fast spectroscopists in this room who've looked at very fast events, and you can indeed follow very fast dynamical events, but you're confined to looking only at one part of the problem in such cases. You're looking essentially at the electronic excitations or the vibrational modes or whatever, depending on whether you're doing infrared or optical spectroscopy. And you're often quite blind to the deeper structural issues of where the atoms are, actually being able to locate them. So what I'm going to make a pitch for is to make measurements with X-rays that actually give you information about as much as possible about the system. But I would never suggest for a moment that you want to measure systems only with X-rays. I would say you really need to use multiple modes of measurement in order to fully understand a system. So infrared spectroscopy, optical spectroscopy, X-ray spectroscopy, X-ray diffraction, all of them should be brought to bear on these critical problems of interest. So some of those critical problems include understanding, whoops, I keep doing that, understanding light harvesting in natural photosynthesis, but also in artificial photosynthetic systems like solar cells, etc., where there are a whole range of processes going on, from the initial formation of an exciton to its separation to the motions that then reset the system so it can absorb another photon. All of those things are in a complex series of events where there are steps in that at many different timescales. So you need to make measurements on many different timescales, both at these very fast electronic timescales, but also at much slower timescales, to fully understand what's going on. And then we have a big interest in the possibility to control chemical and physical processes using light fields, and to do that we're interested in sub-optical cycle timescales, as well as the longer timescales that over which the actual control is effective. And other problems like radiation damage of biological molecules is also, I think, one where there are many timescales that you would like to access, including these very fast initial electronic events, and to understand how those connect then to these longer timescale outcomes. So that sort of sets the scene and motivates us to say, well, we need some ultra-fast measurement technology that can access very fast events, that can access the electronic state and also the structural information of the material. And that's really where we want to apply our ultra-fast X-ray. So this is a restatement of the same thing. My own interest is on this attosecond timescale dynamics. When I say attosecond timescale, I usually mean 10,000 attoseconds or 1,000 attoseconds, which is actually a femtosecond or 10 femtoseconds. But still, we like to use the techniques that have been developed through attosecond science to address these very fast timescale processes. Other colleagues are working on structural changes in light-sensitive protein molecules, or on the photo control of strongly correlated materials. So looking at superconductivity induced by terahertz and optical fields of transiently, the sort of work that Andrea Cavalieri is doing in Hamburg and Simon Wall is doing in X-ray. Okay. So this comes to the point of X-rays. We want to be able to make incisive measurements of time-dependent structure and dynamics using X-rays, using a pump probe scenario. So essentially the idea is you might come along with an optical light pulse to excite the system into some non-equilibrium state, and then you watch its evolution by repeating the experiment many times with a delayed X-ray pulse that interrogates the structure, the electronic states, the spin states, and the other things that may be changing, and returns information for you. So what are those probe modalities that are enabled by X-rays? Well, essentially there are two big classes: X-ray diffraction and X-ray spectroscopy. Now there are many subclasses within these, and I'm maybe grossly oversimplifying them, but traditionally X-ray diffraction has given us a window into the structure of materials. In particular, if the materials are crystalline, so they're well ordered, you get very strong Bragg diffraction that allows you to retrieve the atomic scale structure with great fidelity. Now, as we will see, if you have a bright enough source, you can even retrieve the structure of non-periodic materials, as long as you have a bright enough source and you apply it in the right way. The other modality, so basically X-rays give you the structure and potentially the structural dynamics, how things, the atomic scale structures move. But to understand the electronic states, we can use X-ray spectroscopy. And again, there are several modalities of X-ray spectroscopy that one employs. The key thing about X-ray spectroscopies is you use the atomic specificity of particular absorption features. So if you're at your X-rays are resonant with say the K-edge in a particular atom in your structure, so this is the K-edge corresponds to a photon exciting from the innermost state of the atom into the continuum or the valence states just below the continuum. So for carbon, that energy transition is 285 electron volts. So if you can tune your X-rays to look around that energy, and therefore look locally around the carbon atoms and what the electronic structure is. Or if you want to look at that metal center in that ligand metal complex, you could look at an edge in the metal and use that to locate the electronic structure in the vicinity of the metal, because the dipole moment is large in the vicinity of the metal. But there are other modalities that you can use, as well as X-ray absorption spectroscopy. A lot of work is now being done on X-ray fluorescence and RICS, so photon in, photon out kind of techniques that allow you to again look at the excited states in a time-dependent method, and then there's a whole class of photoelectron spectroscopies, photoelectrons directly, or Auger electrons that can be looked at. And together with X-ray diffraction and those other X-ray spectroscopy techniques, you can kind of get a lot of information about what's happening to both the positions of the atoms and also the electronic states as they evolve. So what you need to do that, now all of these techniques of course are widely applied and have been widely applied for decades. They're what synchrotrons do very, very well. But with synchrotrons, of course, the pulses are relatively long, so you can't access, in general, the fastest dynamics. So to access the fastest dynamics, you need to do the sort of pump probe measurement that we just referred to, using a short X-ray pulse as the probe. So we now need to consider what the options are for short X-ray pulses. And in my world, I would say there are two main contenders that seem to be making really interesting progress at the moment. One is high harmonic generation, HHG, driven by strong laser fields, which generate short wavelength light. And we'll talk about that one first, and I'll show you a few examples of work, mostly from my own lab, which is exploring that. They have some limits. They are typically only going to be good up to about 500, 600 electron volts at the moment, so pretty penetrating only the soft X-ray range, but already giving us access to the carbon, the nitrogen, and the oxygen K edges. They're not very bright. They only have about 10 to the 7 photons or less per pulse. It means that you're really confined to the regime of doing linear spectroscopy, not non-linear spectroscopy at the moment. But they do have excellent coherence and synchronization with the field that generates them, and they can generate very short isolated pulses. Sub 200 attoseconds have been demonstrated in many labs. So I'm going to talk a little bit about that in a moment. The other route is the X-ray free electron laser, and we've only had true X-ray, the so-called SASE free electron lasers, for about a decade, and they've made a huge impact already. So basically, in this case, X-ray free electron lasers can make pulses as short as a few femtoseconds long, and in fact, just recently, in the last year or so, sub-femtosecond pulses have been demonstrated. They have a very high energy tuning range. At the cost of needing a very expensive machine, you can get to 10 keV photons or even higher photon energies. So you can really access a very large range of photon energies using an X-ray free electron laser. And they typically give you many more photons per pulse, so they open up the possibility of doing non-linear spectroscopies as well as doing efficient diffraction measurements. So we'll come to those in a moment. I first of all want to give you a quick review on what some of the current work with high harmonic generation is. And in this talk, I'm going to say a little bit about other people's work and a little bit about the work going on in our own lab. And I'll try and give you a survey, but it's incomplete. So please realize I'm going to leave out a lot of very important work that has been done, but there's simply not time to review. So I should say, before we move on and talk about these X-ray sources, a lot of very exciting work is now being done using ultrafast electron diffraction. So in the last couple of years, there's been really some significant advances, in particular with a relativistic electron gun developed at SLAC, which is now being open to user operation. So one can anticipate in the next few years, time-resolved electron diffraction becoming a much bigger and more important technique. But at the moment, it's not reaching this few femtosecond temporal range, so I'm going to, for the moment, not talk about it, at least not today, and we'll concentrate on the X-ray. So how does high harmonic generation work? Well, the typical model of high harmonic generation is you expose an atom to a very, very strong laser field. That's this electric, this yellow line, that represents the electric field of the laser. So that's almost a cycle of the field. And remember, the cycle of an optical laser field is typically about 2 femtoseconds, depending on the wavelength. So it's really already a fast clock, if you like. That, at the peak of the field, causes tunnel ionization, so you can have a tunnel ionized electron. The electron gets accelerated in the laser field, and then as the laser field changes direction, it will be brought back to the hole it left behind in the atom or the molecule, and it can then recombine, giving up the excess energy it acquired from the field. And that excess energy, as we can see, can be many hundreds of electron volts. typically 10 to 100 multiple hundreds of electron volts. And then it emits that light in a very short burst of X-rays, such that the duration of that burst is less than 1/10 of the optical cycle time. So we're talking about something like 200 attoseconds long. Now typically you would have many cycles of your strong laser field. The way we do our experiments is to make just a few optical cycles, so only one of these events really happens for the highest photon energies, and that allows us to make isolated X-ray pulses of very short duration than those. So that's just an aside. I'll tell you more about that work in just a second. But what's enabled this is the ability to make at different photon wavelengths very strong laser fields. And what's made the breakthrough for making strong laser fields was the ability to amplify very short pulses. So what we need to do to make a strong laser field, we have to confine it in space by focusing it, and confine it in time by using a very short light pulse. But you can't amplify a very short light pulse in a conventional laser amplifier, because it will just burn the material of your laser. So you'll spend €500,000 on your laser and then burn it in the first shot, which isn't a good plan. So the breakthrough that made all of this strong field work possible was the invention of chirped pulse amplification in 1982 by Donna Strickland and Gerard Moreau. And what they did essentially is to dispersion control the pulse, so that they took the full spectrum of a short pulse, delayed different frequency components by different amounts, so they chirped the pulse using a pair of gratings. That allowed them to stretch the pulse by a factor of 10,000, and that then allowed them to amplify that pulse without any danger to their optical components. And then at the end, they can simply use a reverse of that dispersion with another pair of gratings to put the pulse back together again. And this was published in 1982, and as you will all know, it won the Nobel Prize for Donna and Gerard last year. And it was the first Nobel Prize. Donna's Nobel Prize was the first Nobel Prize for a woman in 55 years, and only the third in the history, in physics I should say, only the third in the history of the physics Nobel Prize that went to a woman. So that was, I think, long overdue, and it was a fantastic piece of work that led to it. And I'm very happy because tomorrow at 10 o'clock, Donna's coming to visit my lab. So it will be nice. It's the first time I've seen her post-Nobel Prize. She has visited on quite a few occasions before that, partly in her role as president of the OSA. Okay, so basically we can then generate a spectrum of high-order harmonics using this process. The way the spectrum looks is as a sort of a plateau of many harmonic orders with a cutoff determined by the ponderomotive energy, or 3 times the ponderomotive energy of the electron. That's the amount of average energy an electron gets in a laser field, and it scales as the intensity times lambda squared. And going to longer wavelengths for the drive laser makes it possible to go to much shorter X-ray wavelengths. The cutoff scales in that slightly counterintuitive way. And we use that in our experiments, and I'll show you how, to get to the X-ray absorption edges. So let's remind ourselves again, why do we want to go to X-ray absorption edges? They give us this local electronic information. We can make a transition from one of these inner shell states into the near to continuum states, the unoccupied valence states, or the low continuum states. That returns a huge amount of information concerning the electronic state of that system, and you can do it by choosing the X-ray wavelength to be at the resonance for a specific atom. You can actually localize that probe, and you could even use multiple different X-ray wavelengths to look at different edges and different atoms. So these are typical X-ray L-edge spectrum, K-edge spectrum, and the action is the stuff we're interested in is near this edge. It's just in the pre-edge and just above the edge that we look to try and understand what's going on. So we want to be able to make very short X-ray pulses that can look at, say, the K-edges in materials like carbon, nitrogen, and oxygen, and also maybe probe L-edges too in a large number of elements. So to do that, we've been working in my laboratory, and we're not the only ones. Other labs around the world are working on this, notably here in Spain at IQFO in Barcelona. Jens Bigert's group is looking at this, and Zhenggu Chang in University of Florida, and a number of others are working hard on exactly this topic. And so we had a kind of a breakthrough a couple of years ago when we were able to show how we could maximize the flux in the generation of isolated pulses inside the so-called water window. The water window corresponds to the gap between the oxygen K edge at 285 electron volts and the carbon K edge at 285 electron volts and the oxygen K edge at 540 electron volts, in which water is essentially transparent. And so we optimized our longer pulse, short pulse, few optical cycle pulse laser for that generation, and we're able to demonstrate the generation of isolated attosecond pulses across that water window, and with relatively high flux. And we published a paper last May on that topic. And one of the things we were very pleased with was that we could actually use this light source to measure something. Because, you know, making short pulse light, you know, there's been many records claimed and then no one's done anything with the light source. Well, in this case, we immediately went and measured for the first time with an HHG source the XANE spectrum, this near-edge absorption spectrum in oxygen. So this is around 540 eV, and we pick up some of the pre-features. This is in a mylar film. We pick up this pi star pre-edge feature. We pick up additional sigma star features just above the continuum edge that are characteristic of the material and give information. This isn't a time-resolved measurement. This is actually a very time-integrated measurement, because as you can see, there are big error bars here because we don't have a lot of flux at the oxygen edge. So we have to integrate over many, many minutes to build up a spectrum. So we haven't yet done time-resolved work at that edge. However, at the lower edge, at the nitrogen edge, we get really nice, nitrogen edge is about 410 electron volts, and already here we get really nice, well-resolved, you can see a converging Rydberg series in this nitrogen molecule, which is really nice and is well-resolved. So we turned that to look at some interesting materials, and one of the materials we've been looking at, and this was work done with my PhD student Alan Johnson, who's now working with Simon Ward in IQFR, was to look at P3HT, which is a polythiophene polymer, which is a base material for a number of organic photovoltaics. And so what we're interested in is understanding the exciton dynamics in such a system, because that's key to understanding optimization of function of photovoltaics. So we started by looking at the static carbon K edge and sulfur L edge spectrum of this system, and got some very well resolved spectra, which were better quality than other that have been published in that material before. And now the current state of our work is trying to do some time resolved measurements on this. So to use, we have a pump probe beamline which was assembled and put together under my ERC grant, and we're basically pumping this material at the excitation frequency, which is about 600 nanometers, using a short pulse in one arm of this delay line, and then we can look at the difference between the unpumped sulfur L edge spectrum and the pumped sulfur L edge spectrum, and there are really big differences. And in particular, we see one of the pi star features on that pre-edge get really much weaker because it's now had an excitation into it. So it has, by looking at that decrease and how it then relaxes, we get information of how quickly the exciton decays. And so that's what I'm going to show you in the next slide. Unpublished data, so this one will be expunged, I think, from the final version of this talk. We're still trying to repeat these measurements, but nevertheless, you can see that the pi star feature here at time 0 is the reduction in the absorption, which is encoded in this deep blue color, is gradually relaxing over a period of about 300 femtoseconds as the exciton decays. And so that's a subject we're following up, and a number of other studies have now been published by various groups, including the Leone group in Berkeley and Jens's group as well, looking at different condensed phase materials, measuring ultrafast dynamics in those, using high harmonic generation for time-resolved X-ray spectroscopy. Now, how long do I have, Rebecca?
15 minutes.
Oh, 15 minutes. Okay, I better move on to the second topic. I better move on to free electron lasers. Before I do, I'll skip this slide. Before I do, I'm just going to mention one of the things we're excited about in the HHG community is the possibility of using brighter sources of HHG, and one of those has been built in Hungary, at Szeged, in the Eli Alp program. Here's a picture from November in which Gerard Mourou, who's standing here giving a speech, is about to unveil a plaque to commemorate his and Donna's Nobel Prize, and it's on the pavement on the way into this facility in Szeged in Hungary. And there's a whole, it said in the pavement, a whole bunch of memorial stones, so all the Nobel Prizes that led up to the high power laser facility, so they just added an extra one that Gerard got to unveil in November. Okay, so the other way we can make very short pulses of X-rays is using an X-ray free electron laser. Now, an X-ray free electron laser relies on having a low emittance, narrow energy spread, relativistic electron bunch. Typical energies used in the functioning free electron lasers are between 4 and 15 GeV. So that probably tells you that that's quite a special instrument and requires a certain amount of resource to build it and maintain it, but I'll say more about that in a minute. The way the X-rays are generated is in a series of undulators. What the undulator does is wiggle the electron bunch around in the magnetic field, the alternating magnetic field in the undulator. As it's wiggled around, it radiates. The back reaction of that radiation in this SASE, self-amplified spontaneous emission mode, leads to a micro-bunching within the electron bunch, a micro-ordering, and it's that, as you progress through the undulator series, that leads to the emission of coherent light, because it's sort of an organized electron bunch, self-organized electron bunch. And at the end of a series of undulators, there may be many meters worth of undulators, typically 50 meters worth of undulators or more. You end up with an intense, coherent X-ray emission. I won't say much more about the generation. I will say about the characteristics. Pulses less than 10 femtoseconds routinely generated, very narrow spectral bandwidth, on the order of not quite getting to the transform limit, but nevertheless quite short and narrow in energy spread. And the good thing is, if you build your X-ray free electron laser right, you can cover a large photon energy range. So the original original free electron lasers were built were in the infrared, and then the vacuum ultraviolet and the XUV. And the first X-ray free electron laser using this SASE concept was the LCLS, X-ray free electron laser, based around the Stanford 3-kilometer electron linear accelerator. They used, in fact, just the last kilometer of the electron accelerator. The first 2 kilometers are now being emptied out of the old accelerator modules, and a new superconducting accelerator is being installed back there for a higher rep rate version of this X-ray free electron laser that will open in about 2.5 years' time. But the existing system, I say existing, it's shut down temporarily for that upgrade, but the existing system is a kilometer of electron accelerator, a few hundred meters of undulators, and then 2 experimental areas for soft X-rays and hard X-ray science. And this was the first to operate in 2009. The second to come on stream was the Sackler one in Japan. The third, the third dish was the XFEL in Hamburg, and this is the first fully operating superconducting system that gives a high repetition rate of X-ray pulses. The current LCLS gives 120 pulses per second. In principle, XFEL will give something like 80,000 pulses per second, and the upgrade on LCLS will go up to potentially 1 million pulses per second. So that makes these things more useful. But it's exactly in April the 10th, there will be exactly 10 years to the day since the first X-ray lasing was achieved at LCLS, and there's a celebration going on there on April the 10th. And I'm glad to be able to go there and join in with other colleagues to celebrate 10 years of this wonderful machine. And a lot of work has been done on that machine and others. I'm going to very quickly survey it. A lot of work, for instance, on time-resolved chemical reactions, so some prominent papers published a few years ago using the laser X-ray fluorescence techniques and RICs to study ultrafast photocatalytic systems of one sort or another. some very exciting work looking at time-resolving phase changes in strongly correlated materials, where the material is prepared with an optical or a terahertz pulse, and then you can probe the electronic states and the geometry of the material as it undergoes that transient phase change. And a number of interesting papers by the Cavalieri group and others have been published in the last few years. Some very interesting work on looking at matter at extreme conditions, in which the X-ray laser is used either to probe or to heat the material. And in this experiment, actually a conventional optical laser is used to heat the material, and then the probe is diffraction from the heated material. And this is a movie showing the material melting, deduced from the X-ray diffraction, time-dependent X-ray diffraction pattern. Other things that have been done, looking at single nanoparticles and lattice motions induced in those. So this is work by Ian Robinson's group a couple of years ago, allowing them to isolate the individual nanostructure dynamics. And the other thing that's been very exciting is the possibility for using this short, intense X-ray pulse in a new form of crystallography, and it's proving to be very beneficial in serial nanocrystallography. This is one of the big applications. Now, the dream for a long time, and it's still being partially realized, is to be able to image things that are non-ordered crystals or have only limited degrees of order. And the smaller the region of order is, the more photons you need to deduce the structure. So coherent diffraction imaging requires a phase retrieval problem to be solved, which can sort of be solved computationally in modern computational systems. But whereas a crystalline material, you don't need to expose the sample to very many X-rays before you've got enough information to form an image. For a non-crystalline, non-periodic sample, you have to expose it to lots of X-rays. And the problem then is you induce damage from the X-rays, so you can no longer see the initial structure, it's gone. And so this is the static imaging of structures, not time-dependent, but nevertheless, in principle, the question is, well, could you use this very bright, short pulse of X-rays to do the crystallography? And the concept is basically this. So you shoot so fast, you actually don't notice any change in the material you're probing on the timescale on which you're probing, and then it's destroyed after. So the concept is named diffract and destroy. And it works to an extent. So non-crystal samples are imaged before they're destroyed, and the same technique is applied to nanocrystallography, where you fly these nanocrystals through the beam. You destroy them in the process, but it doesn't matter because it's got the diffraction information. And a lot of work has been done over the last years solving protein structures using that. They've actually deposited a significant number of new structures in the protein database. This isn't a huge number compared to the total number in the database, but in 2016, it was only a few years after they first demonstrated the first one, there were already 44 distinct structures that have been solved, and now it's many, many more. But another thing you can do is address time-dependent problems. So a colleague of mine, Jasper Van Thor, is one of those who's working on this and looking at protein, light-driven protein structural changes in photosensitive proteins. So they now made a number of measurements on those structural changes. They have another one they're just about to publish where they've actually photo-excited and then watched the structural change using time-resolved X-ray diffraction. Okay, I've got very few minutes left, so I'm going to now go on to the thing that I've been trying to do with the X-ray FEL, which is to make very, very fast measurements of few femtoseconds to even sub-femtosecond time resolution on small prototypical chemical reactions. So one of the systems we studied in a collaboration was the isomerization of acetylene, which was published a couple of years ago. This was a fragmentation study. We did a momentum imaging retrieval and looked at the initial events of that isomerization from acetylene to vinyl D happening with a time resolution of about 10 femtoseconds. For this, we used a X-ray split and delay technique. We took the X-ray, a single short X-ray pulse, put it onto optics that would basically split the wavefront in half has delayed beam-line for those two. But there are now more sophisticated methods for generating double X-ray pulses, and one of those methods is the so-called fresh bunch or fresh slice mode, where you actually get different parts of the electron bunch to laze at different points in the series of undulators, and then you can make different colour pulses of variable delay between them, and that's an exciting possibility. And we've been working on such measurements on a number of experiments in recent years, and the most recent one we tried was to try and image inner valence hole migration, or a similar process to inner valence hole migration, by using a pump probe method. So in this we excite a valence hole state using a first X-ray pulse, and then we resonantly probe that using a second X-ray pulse, a different frequency, and this is using the oxygen K edge, and we just tuned into a hole of interest and trying to see how long does that transient hole survive. And there's some theoretical work that we did to predict what happens in the particular sample we did the measurement on, which is isopropanol. And in isopropanol, this blue state, which is one of the inner valence states in isopropanol, you make a hole in that state, and you see it shows a very non-exponential oscillatory decay. This is akin to that charge migration that was seen in that peptide. And so we said, well, can we make that measurement of that evolution in that state? And the answer is yes. This is the first time I've shown this data. We took over a year to fully analyze it, and I know it's kind of a bit noisy, but basically we see a transient hole. So this is basically the whole survival, the whole yield. It turns on and then it decays away over a period of a few femtoseconds. And the red curve is based upon our calculation of what it should do. Now, this is work that we're still analysing, but in the future we would like to make better measurements. And to make better measurements, we're going to need a better machine. And that's expensive, because these machines are, of course, very, very expensive to build. The budget for the Euro XFEL was somewhere significantly north of €1 billion. And so we're very grateful to the Americans for building the next machine that we're going to use, which is the LCLS2. And the ways that we need to do better is in two ways. First of all, we need it to actually have a shorter pulse. And the second way is we need more pulses per second. And then we can clean up the statistics on this and get a much tighter time resolution and really measure the oscillatory value. And the shorter pulses have already been achieved, both in the hard X-ray range. So the first demonstration of 200 nanosecond pulses was made in 2017 at LCLS. And then in the soft X-ray range, experiments were completed at the end of last year, just before they shut the facility down, which confirmed that the soft X-ray X-leap mode of operation, as it's called, worked, and it generated sub half femtosecond pulses quite stably, and there's even now a two-color, two-pulse mode that's been explored and investigated, and these will become available on the upgraded machine when it operates again. And I think I should stop now. I must be coming towards the end, so let me move towards a conclusion. So looking ahead, I think the X-ray free electron lasers are offering many new routes to ultra-fast measurement. Of course, my own interest is this very fast timescale, but even at less high time resolution timescales, the high rep rate is going to have a huge impact in terms of the quality and the type of system that can be measured. Hopefully one can now measure very dilute samples in solution as well as high time resolution. So Euro XFEL, which is now operational, is looking very promising, and LCLS2, which will go up to 1 megahertz as is hoped, is really going to be pretty revolutionary, and that looks pretty bright for the future. And at the same time, we will be having facilities, laser facilities like Eli Alp in Szeged. So I think that we will be able to move forward with this science even faster over the next decade or so. So as a conclusion, both HHG sources are enabling high-quality X-ray time-resolved X-ray spectroscopy, and now are being applied to condensed phase systems. Time-resolved X-ray diffraction and spectroscopy is showing great promise in unraveling the sorts of structural dynamics questions we raised at the start, and there's real push towards even higher time resolution and better statistics in the measurements, so we can really resolve very fine effects. So let me conclude and thank you for your attention.
Thank you very much, Jon, for this very illuminating talk. There is some time for discussion or comments. Very silent audience.
Where do you see the field with the high harmonic generation? What do you think it will get in the next 5 years? Will it get a kilovolt?
I mean, of course, kilovolts and even 5 kilovolts have been claimed, have been observed. I mean, not just claimed, but observed, but with very, very low flux.
Yes.
And that's the problem. The flux is so low, you can't make a measurement with them. And so I would say, at least my own goal at the moment, just to consolidate what we can do in the water window, but look for ways to improve the flux, and maybe a higher power drive laser is a solution. Now, one of the things we learned in our work to generate the oxygen K-edge was that, in fact, using these somewhat longer drives really complicates your understanding of what's going on. Well, in the end, we understood what was going on, but only by building a full numerical simulation of all of the ionization and laser defocusing dynamics that went on. It turns out that because your longer wavelength is much closer to the plasma frequency of the free electrons, you have a much more dispersive medium, and that really causes things to be a much more coupled problem. And so we a little bit reluctant to make predictions as to how, when you go, say, to Eli Alp, and you have maybe 10 times the peak laser power, would that translate to a cutoff which is 10 times higher? It's not clear that that will be the case. But, you know, as our understanding of the process grows, we might be able to find robust scaling strategies. But I don't think it's going to go very fast, because we've been trying already for several decades to go to those very high photon energies. But I think now, in the last few years, we've at least nailed up to the oxygen K-edge.
About the LHs of the transition metals?
Some of those we can access, I believe, and you know, I think I'm reasonably optimistic of being able to go to about 700 EV with the current technology. So I think we can start to capture some of those. So that's still the hope.
Let me ask you something, Jon. Then, in a situation like the whole dynamics, no, in this isopropanol, no. You showed the noisy experimental data and this nice red theoretical prediction. How good is theory in a problem like that? No.
Well, actually, let me be honest now. Now I'll be honest. This theory is theory that had only the electronic dynamics in, and that's done at a very high level of electron correlations using ADC2. It's actually fully correlated electrons. So in fact, so much as the electronic structure is static and classical, it's very accurate. But of course it's not. And there are two things that come in. One is that, of course, the nuclei can start to move, and there are protons involved in this molecule, and they move really quite fast. And the other is you have already coupling your, basically why you're getting this oscillation is because you're creating a coherent superposition of two or more electronic states. But these electronic states don't have a single energy separation, because you need to think about how the nuclear wave function is sampling over multiple different values of internuclear coordinate. And that changes, because of the slopes on the potential energy surfaces, that changes the spread of the energy separation. So you actually have an inherent dephasing that causes a decay of the electronic coherence. So this is a sort of a more or less perfectly coherent system, and that's the maximum coherence, but that will be damped by those nuclear effects. And we put in, let's say, an empirical value for that damping, based upon some calculations that Morgan Vacher done, in order to get this red curve. So yeah, I think what we would really like to do in a measurement like this is do a much better measurement with much higher temporal resolution and better statistics, and 100 kilohertz machine would make that really much easier. And then to look at more sophisticated calculations.
I'll ask you one more thing then. I realize that Attosecond science still has a world to explore, but is there anything next? If we manage to make pulses of a fraction of an attosecond, would there be a problem?
A lot of discussion is made about zeptosecond science going to this next time domain. It's not going to happen in my generation, so I don't spend a lot of time worrying about it. But nevertheless, I think there are some interesting problems in terms of nuclear physics that might actually be addressed. Photo interactions with nuclei do happen on very fast timescales. So that could be one area where such very fast timescales are applied. My own vision for the attosecond science, and here I mean few femtosecond time resolution or maybe a bit faster, is that actually there's so many more complex systems that we can explore now we've developed the technology. So this is a small molecule, but it's a stepping stone to looking at more complex, larger molecular systems, condensed phase systems. So I'd say that for the next few decades, that might be where most of the effort goes, and certainly that would then open attosecond science techniques up into making real impact on other scientific disciplines.
More questions? Okay, in that case, let's thank Jon again. Edition of the colloquium will be at the end of April. We will have Gerard Toft, winner of the Physics Nobel Prize, and we hope that you can be here too. Thank you very much.